Unit 11, Day 3 notes, solving log equations. The warm-up asked you to write the description of the transformation for g of x from f of x. If you're watching this as a video, pause, try it, and then unpause. All right, so we have got 3 values to identify in here that were not in just the parent natural log of x. So the 1/4, that is A, H, or K. Which one is that? A, good. The coefficient in front being multiplied in front of your log, that's your A value. And that tells you your vertical stretch or compression if that A is something other than 1. Okay, so this is a vertical what? Compression. When A is between 0 and 1, which 1/4 is, it's a compression. Very good. If it were negative, it would be a reflection over the x. This one is not negative, so no reflection. Okay, the next value we need to identify is that 12. Is that H or K? And it's inside with the x. Good. And remember that the H is the opposite sign that you see there because it's x minus H. So H is actually positive 12, which tells us our graph has translated right 12 because H is our horizontal shift. And then the last one is the 6. That is your K. That is your vertical shift. It's added on the outside and it is a positive. So it tells us our graph is shifted up 6. If you got those, fantastic. If you didn't, make sure you correct mistakes you had or add in the ones that you missed. And just make sure that you keep practicing this. Remember, we had an ALEKS assignment assigned on Wednesday. If you did not finish that yet, you need to finish it by Sunday. Remember when it would normally be due today, but since it's a Friday, I'll give you all the weekend to finish. So just get it in before 11:59 p.m. Sunday is the deadline. All right, so let's start looking at this new stuff. We have, if you look at the notes front and back, there are 3 different ways that we're going to go over how to solve log functions or log equations. Okay, so the first one is using equivalent bases. Okay, so solving log equations using equivalent bases when the equation is written or can be written in the form log base b of something equals log base b of something. This is very similar to our notes that we did on exponentials. And I'm actually going to pull those up real fast. Back in Unit 10, when we did exponentials, let's see, solving. Oh, why don't I have a completed one? That's weird. Day 3, those are all blank. Or day 2. Okay, well, I'll look at the blank ones with you. I don't know where the completed ones are. I'll have to go find those later. Okay, but back here, when we did Unit 10, solving exponentials, we had this same property. We said that if you have matching bases of your exponentials, then that means that the exponents must be equivalent to each other. Okay, that was the same concept that we're looking at here with logs. This is saying if you have a log with the same base on both the left and right-hand side, that what you are taking the log of must be equivalent. Okay, this is our one-to-one property. Okay, it was the one-to-one property of exponentials. Now it's the one-to-one property of logs. Okay, so I'm going to write that here. I'm going to say this is using the one-to-one property. So if you have the same log base on the left and the right-hand side, and there's nothing extra, No coefficients, no constants added on the outside, just log of something equals log of something, and the base of the logs matches, then what we are taking the log of must be equivalent. Now it says x, y, and b have to be positive, and of course b cannot be 1. This does not mean when we solve any of these, we can't get a negative number. It means when we plug it back into whatever this expression is in here, this cannot come out to be a negative because you can't take the log of a negative. Okay, we talked about that in our day 2 notes for logs when we did the graphs and we talked about the domain and the range. We said that the parent functions for the logs had the vertical asymptote at x is 0. And the graph was to the right of that. The domain was 0 to infinity. You can't take log of a negative. If you try to take log of a negative in Desmos or in your calculator, you're going to get an error. Okay. All right, so let's try to apply this property. We have in A, log base 2 of 5x minus 9 equals log base 2 of 2x plus 6. So because these logs are the same base, they're both a log base 2. I don't know why the L didn't highlight. We can then assume that what we are taking the log of must be equal. That's what the property tells us. So essentially, you are just dropping the log. You're just saying, okay, 5x minus 9 equals 2x plus 6. Now it becomes a basic algebra problem or pre-algebra problem, really. Solve for x. We want to get the variables to the same side, the x's to the same side. Subtract 2x, because we use opposite operation. That leaves me with 3x. I've still got the minus 9 equals 6. Then I move the constant over to the other side, away from the variable. 3x equals 15, and then I divide out the coefficient. How have I said all year long with all the different functions we've worked with, how can you check to see if you found the correct solution? What can you do with that? Plug it back in. You can always take your solution, plug it back in for we're saying x is 5. Go find x and plug in a 5 and see if this actually comes out true. This should come out equivalent. The left should equal the right. So if I were to plug in a 5 here, 5 times 5 is 25, minus 9 is 16. So I end up with log base 2 of 16 on the left. If I plug in a 5 over here, 2 times 5 is 10, plus 6 is 16. So log base 2 of 16 on the right. So it checks out. Using that, plugging in and seeing if it makes it true as a way to check, great. If you have a multiple choice question on a quiz or a test, though, that also means you could just take your answer choice and plug it in and see which one works. Which answer choice makes the equation true. So you can work backward when you have a multiple choice question as well. All right, let's try B. In example B, we have the same concept, except this time it's natural logs. I don't see a base, but when we have a natural log, what's the understood base? ln is the special notation for natural log, and we use that when we have a base. No, base 10 is common log. That's what we've got going on in C. When you have log, but no base is written, that's an understood base 10. When there's no base written, but it's a natural log, that was the base E. Okay. In this particular problem, that doesn't come into play, but you do need to know that. So they're both a natural log, so I know that they're the same base. They're both a base E. So I can essentially eliminate them and just have x over 2 equals 4x minus 7. If I want to solve for x, I first need to get rid of this denominator on the left. So how am I going to get rid of divided by 2? I'm going to multiply, opposite operation. So times 2. Now what you do to one side, you do to the other, but I can't just do this and just multiply the 7 by the 2. The entire other side has to get multiplied by 2. So we put parentheses around that, and we're going to have to distribute the 2 to both terms over there. So that becomes 8x minus 14. Now I'm going to move my x's to the same side. So I'm going to subtract the 8x to the left, which leaves me with negative 7x equals negative 14. And I'll divide out that coefficient of negative 7. A negative divided by negative is a positive, and I get 2. I can always come back up here and test it out. 2 over 2 would be 1. So I'd have the natural log of 1 on the left. 4 times 2 is 8, minus 7 is also 1. So I have the natural log of 1 on the right. So it checks out. X is 2. All right, in C, I already mentioned that these are both common logs. They're understood base 10 logs, which means what I'm taking, since they're the same log on the left and the right, I can eliminate them and just leave myself with x plus 4 equals 7x. So then I'm going to subtract this x to the right and then divide out my coefficient. This does not divide evenly, but I can reduce the fraction. What is 4/6 reduced to? 2/3. Very good. And if we checked that, it would check out as well. Okay, so that is one-to-one property. And I think that is the easiest way to solve logs, but it will only work, thank you, it will only work if you have the log on both sides of your equation. Okay, it's got to be set up in this format here to be able to use this way to solve. Okay, so sometimes you can't use it. Sometimes there's only one log expression in your equation. So let's look at some alternate ways to solve. Okay, so this one says solving using inverse property, exponentiating both sides. So I'll give you a forewarning here. I don't like this method. I'm going to show it to you because it works. It is an option, but I don't think it's the easiest method, and it's never a method you have to use. There's always an alternate method than this one. Okay, so if you can solve it using this method, you can also solve it using the method I'm going to show you after this. So if it seems confusing, don't worry, I'm going to show you another method as well. So solving log equations by exponentiating if the equation contains or can be written with a single log. So when there's a single logarithm, you can use this method, or if it's written in the form we just talked about. So the thing is, exponentiating will work whether there's a log on both sides or there's only a single log. Okay, so that's the one benefit of this, is that it'll always work with a single log or the two logs. Okay, so the process is to isolate the logarithmic term. Okay, so if we're dealing with a single log, you isolate it and then you exponentiate both sides to unlock the variable. Okay, so to get the x out of the log, okay, out of the argument of the log. Okay, so it says to remember to use the same base as the log term whose argument you are trying to unlock. Now, what this is creating, I'm going to have to go back and show you in our exponential notes. or I'm sorry, our day one log notes. This is what we're trying to do here. The part that's highlighted in pink. We talked about this in the intro notes. We said if you have some value or base, that's B here, raised to the power of a log with that same base value, that those are going to reduce to a 1. And you're left with just the argument of the log, just whatever was here. That's all you're going to be left with. Do y'all remember that? We talked about that. We practiced simplifying some of these. Okay, so that's the whole point of what we're doing here is we're going to rewrite it in this format to get rid of the log so that we can reduce and get rid of the log and just be left with the argument to solve for x. Okay, so that's the goal here. I'm going to write that off to the side. We're trying to get a base raised to the power of log base b of x so that we can just be left with the x. That's the goal of exponentiating. Now, in example 2a, we're going to try that. The first step is isolate, though. Isolate the log expression. That means if there's a coefficient or a constant added or subtracted on the outside, those need to move. So in this case, there's a 4 and a 2 that both need to move away from the log expression. Okay, in B, my log expression is log base 5 of 6 minus x. So there's a +1 that needs to move. The 6 does not move because it's inside the parentheses. It's part of the argument, part of what we're taking the log of. So when we say isolate, I need you to understand that difference. If there's a number added or subtracted not in parentheses, it's going to move. But if it's inside the parentheses, it doesn't move. It's part of what we're isolating. You'll see the difference? All right. So in A, I'm going to isolate natural log of x. I have to move the constant first. So I'm going to subtract the 2. And then I got to get rid of the coefficient of 4. So opposite operation is to divide. So I'm left with the natural log of x equals 8. Now, when it says, that's step 1, isolate the log expression. So I got the log expression by itself. Now, step 2 is the exponentiate. So this means whatever our base of the log is, we're going to write the left and right side as powers on that base. What is the base of a natural log? What did we say earlier in the notes today? If it's a natural log, it's an understood base what? No, we just talked about this up here. I said we didn't end up using it here, but when we were matching these, what did I say the base was of those? E, thank you. Okay, so this is a base E. Even though we don't see it, it's a base E. So we are going to write E to the power of the natural log of x equals, and what you do to one side, you have to do to the other. So we have to put base E and make 8 the power. We talked about how if you have matching bases, what's in the exponent must be equal, right? So this is like going in reverse of that. Instead of getting rid of the bases and setting the powers equal, we're making what is set equal into the powers, okay? Now, the whole point of doing that is so that, get a highlighter here, this base matches the base of this log. This is natural log base E, and when that happens, that is going to reduce. And we're going to be left with just the x. So x is e to the power of 8. Now I have solved for x. Now it says up here in the instructions to give both the exact solution, which e to the power of 8 is, that's the exact solution, but it also wants us to approximate our solution to 3 decimal places, 3 places after the decimal. So if I come here and I type in e to the power of 8, I get 2,980, and then 95798. So 3 places is where the 7 is. Is it going to stay as 7 or is it going to round up? It's going to round up because of that 9. You always look one more place to the right to see if this should round up or not. So it's going to be 2980.958. Remember, when you see those squiggly equal signs, that means approximately. That means this value is approximate. It's not exact. This is a rounded value. So we got the exact value and the approximate solution. Feel okay about that? Let's try that process with B. We want to isolate the log expression. I've already highlighted it, so I need to subtract the 1 over. So I've got log base 5 of 6 minus x equals 2. Now, to exponentiate, we need to know the base of the log. What's the base? This one, it's not a hidden base. It's not an understood base. It's there. What is it? It's 5. 5 is the base of the log. So we're going to write 5 to the power of log base 5 of 6 minus x. And what we do to one side, we do to the other. So we need to write 5 to the power of 2. Now again, what happens there? What this allows me to do is say that this base 5 and this power of log base 5 are going to reduce and simply leave me with 6 minus x. And it equals 5 squared. What is 5 squared? 25. Now I can finish solving for x. So I'm going to subtract the 6 over. Divide out the negative. Now here's where I was referring to at the beginning when I said what you take the log of cannot be negative. That doesn't mean your solution can't be negative. So let's double check. If I take this negative 19 and I plug it in for x, 6 minus a negative, what's minus a negative? What happens when you subtract a negative? What does it become? Anybody? No, I don't think so. Nobody? What happens when you subtract a negative? Remember, the notes go faster when you participate. Minus a negative. Double negative. Becomes a positive. It becomes plus. Thank you. So 6 minus negative 19 just is 6 plus 19. So you end up with a positive number here as the argument. So you're taking log of a positive. So it's okay that your solution was negative. When you plugged it in, your argument still came out positive. Okay, it's the argument that cannot come out negative. So just make sure you understand that. All right, now in C, this one is different. Up here, we said we can use this method when there's a single log function, like in A and B, or when you have it set up with the same log base on both sides. So yes, we could use one-to-one property here, like we showed you in example 1, but I'm going to show you, you can also exponentiate with these. Both of these are a log base 10. There's no base written here, and so it is an understood 10. This is the common log. So I can write a base 10 to the power of log of 5x equals a base 10 to the power of log of 4x plus 7. And on both sides, base 10 to the power of log base 10, I know is going to eliminate or reduce and leave me simply with the 5x equals 4x plus 7. Now, I told you earlier, this is not my method of choice. It's a method that works. It makes sense. It uses all the properties that we've learned. But in this case, that's an extra step. I could have gone straight to this line using one-to-one property, couldn't I have? Y'all see that? Knowing that this is a log base 10 and a log base 10, I know then that 5x must equal 4x plus 7. So again, I think this method here is pointless because it's just an extra line of work. Okay, I would have gone straight to this line in red had I been using one-to-one property. But now you solve it the same. You get the x's to one side. And that comes out to just x equals 7. And you can check it if you need to. I'll let you know it does check out. All right, so that's one method for solving when you have a single log expression or when you have it set up like a one-to-one property. But again, I'm not going to probably ever solve this way. This next method is my method of choice when we have a single log term. Okay, so when we have a single log term, you can always rewrite the log as an exponential. Okay, so solving log equations by rewriting as exponential if the equation contains or can be written with a single log term. So step 1 is the same. Isolate the log term. Okay, so I'm going to try that in example 3a. So the first thing I want to do is isolate the log expression, which, well, that one's already isolated, isn't it? There's nothing outside the parentheses being multiplied or added. So there's nothing I need to move. Step 1 is already done. Now over here in B, there's going to be a little bit of work to do. There's a 2 and a 5 that are going to have to move for step 1. Now in step 2, instead of rewriting these with the log as the exponent, we can just rewrite the exponential into exponential form. So this is where we're going from log base B of x equals a to base B to the power of a equals x. This is converting or rewriting it from log form to exponential form, and you have to remember what goes where. Okay, this is what we learned in day 1 notes in the intro to logs, how to rewrite. So what is my base here in example A? What is the understood base if no base is written and it's log? Base 10. So this is a 10. And then remember what the log is set equal to is what becomes the exponent. So here that's a 3. And then what was inside the log, what was the argument, is what the exponential becomes equal to. So that's the 3 minus 2x. So now I don't have a log, and I can solve for x. What is 10 cubed? 10 times 10 times 10. 1,000. 10 times 10 is 100, times another 10 is 1,000. So we've got 1,000 equals 3 minus 2x. So then I'm going to move my constant. And then I'm going to divide out my coefficient. So that's going to come out negative. So we've got negative 448.5. Now, is it okay that this came out negative? If I go to plug in a negative, look at that. It's being multiplied by a -2. So the negative times the negative, it's going to become positive and add a 3 to it. So it's okay. It's going to be a positive. You can take the log of a positive. All right. Y'all feel okay about that one? Let me actually, I'll try and do a little highlighting like we did in the day one notes. We said the base was down here. So it was a base 10. And that looks green because it's yellow. Ugh. I'll do the highlighting over here. Okay, so that's like our little conversion thing that you need to remember. All right. Now, example B. We have to isolate the log expression. So I'm going to move the constant, the +5 first by subtraction. So we move by opposite operation. Gives us 6. Now I'm going to move the coefficient that's being multiplied in the front. I'm going to divide it out. So I'm left with my log expression equal to 3. So step 1 done. Isolate the isolate the log. Now step 2 is to rewrite it from log form to exponential form. So what is the base here? 3. This 3. What's the exponent? This 3 became the base. So over here, what becomes the exponent is what the log was equal to. So that's also 3, but it's from a different spot. It just happens to also be a 3. And then that is going to equal, up here, what you were taking the log of is what that comes equal to. So 2x minus 1. So I've got it rewritten from log to exponential. Now I need to solve. What is 3 cubed? 27. 3 times 3 times 3 is 27. So I've got 27 equals 2x minus 1. I'm going to add the 1 to both sides. And then divide out the coefficient. And I get 14. You'll feel okay? All right, this is the method that I think is easier than the one we did in example 2. When you've got a single log expression, I would just isolate and rewrite it as an exponential rather than trying to exponentiate both sides and eliminate. Now, I'm not saying you can't do it that way. Obviously, it worked, but this would be my recommendation. And when you ask me for help or I do any more examples or problems with y'all, this is the method I'm going to use. All right, now last but not least, you can solve by graphing, okay? And you don't have to graph by hand. This is using Desmos, okay? So I have showed you this method with other functions. It works with logs as well. It works with exponentials and absolute value and quadratic and cube root and cube and square root. It works with everything. You can always set the left side of the equation and the right side of the equation as two separate graphs and then see where they intersect. Okay, I've showed y'all that before in previous units, and I'm going to show you again here. So when we say put it in the left and the right side, so the left side of the equation and a right, and then the right side of the equation. In this case, it's just a constant, but it doesn't have to be. It works even if there's a variable over there as well or a log over there. It'll still work. Okay, so I'm going to graph both of those functions on this grid. Now I'm going to use Desmos. I've actually got typed in already over here. Okay, so here's the graph. That's what I'm going to graph over here on mine in the notes. So we've got a constant at 3. So just a horizontal line at 3. And the other one looks like it is the log parent function with a base 2 shifted left 1. So we can see our vertical asymptote is at -1. So if you want to draw that as an asymptote, you can. You don't have to draw the asymptote. It's okay. But then what is normally our x-intercept at 1 is shifted left, so it's at 0. Okay, and we can see we've got another point there at 1, 1. And then we've got another point there at 7, 3. So now I can sketch this curve for this log. So then the question is, after you graph both of them, the question is, what is the point of intersection? Where was that? At 7, 3. What part of that is your solution? What are we trying to solve for? What variable? X. So that's why up here in step 3, it says rewrite the X value of the intersection as the solution. So it's X equals 7. That right there is your solution, the X value. So that's another way that you can solve logs. So you can solve them graphically by putting the left side and the right side as their own functions and finding the point of intersection. If they're single logs, you can rewrite them as exponentials. If it's a log on both sides, you can use the one-to-one property. Okay, those are my recommendations. Graphing can be with either a single log or a log on both sides. You can use graphing. All right, so y'all give this a shot on the exit ticket. Take a minute. If you're watching this as a video, pause and give that a shot. I'm gonna freeze y'all's screen up here and let y'all try that, and then we'll check it. Anybody get a solution yet? 13, very good. Let me unfreeze so y'all can see. So I used one-to-one property. I said it's a log base 6 equal to a log base 6. So what we're taking the logs of must be equal. And then I solved and got 13. If you chose to try this graphing in Desmos, you should have gotten the same point. The point where they intersect should be where x is 13. All right, no new assignment tonight. Y'all just need to finish up that Alex from from Wednesday. That Alex is due Sunday night before midnight. Okay, no new assignment tonight. We will practice this on Monday and then do a formative assessment at the end of class. Then we will take our last set of notes on Tuesday. And then you have a review day. Y'all picked up the review today, though. So you have the review all weekend and next week to work on it. Okay, but this will be our class period to just ask questions about it and make sure you get clarifications on anything that you're confused on. That review will be due on Thursday, which is our test day. Any questions? Okay. Y'all have a fantastic weekend.